Hi, this is Tariq Rashid. Today we're talking about another algorithm, which is a heuristical search. It's called hill climbing. I'll go through the algorithm and I give you example how to work with this algorithm. So first, heuristic search are formalized as rules for choosing the branches in state space that are more likely to lead to an acceptable problem. Heuristical search problem may not have an exact solution and sometimes may not be complete because there is inheritance in ambiguities in the problem statement or sometimes availability of data. For example, we have a medical diagnosis. Now, a problem may have an exact solution, but computational cost of finding it may be excessive. Okay, example of this: games of chess, where state space is continuously growing, and where we cannot sort this problem by depth first search or breadth first search, they may fail to find a good solution within that length of time. Heuristic, because breadth first search and depth first search is a blind algorithm, heuristic attacks can attack those problems and can give you a promising path. So hill climbing, it could be heuristic search. For example, hill climbing, the idea comes from if somebody in hills, okay, if somebody is here, that's not a good drawing. If somebody is here, so it thinks that this is, he can see this one and he can see this one, but he cannot see this one, which is sometimes you can go wrong. Cannot see this is higher than that hill. Likewise, could also be used in the buildings. So if a person is here, can only see this one and this one, but might not be able to see this one. Now, that's the idea of hill climbing. So the algorithm comes from, that's how the algorithm works. We try to evaluate the initial state. If initial state is the goal, quit the algorithm. Otherwise, the current state is the initial state. So it goes point by point, from hill to hill, from a place to another place. So when we get this current state, we try to select a new operator for the state, and we generate new state, new kids, new offsprings, and evaluate the new state. If closer to goal than current state, make it the current state. If it's no better, ignore. And if the current state is the goal state or no new operator available, then quit. So if it's goal, quit. And if it's no new operator, again, quit. Otherwise, you go back to step 2, which you select new operator and reevaluate it and check it again. So that's the algorithm, how it works. If we have this tree, A6, that's distance, so that's root. It has 3 kids, B, C, D. Each one of them has a distance, 5, 3, 4. C to 4 is 4. C to G is 2. And B to T is 1. It's not written here, so that's 1. That is 1. Sorry, that is considered 1, and 1 here as well. And that maybe 1 is here as well. So we try to solve this problem. So next, we have two arrays. This is open list, and that's closed list. Open list, the nodes are waiting to be processed, and closed list, the node has been processed and kind of exhausted. So we throw them to the bin or closed list. So first one begin. We begin with root node, which is A6. We evaluate it. We try to see how many kids has. It has B5, C3, D4. Now we put them B5, C4, D. Now select operator, the shortest link is C3. It's less than D4 and B5. So we select C. So we rearrange. This one comes first and this one comes last because D4 better than B5. So we'll check this one if it's a goal and quit, or if it's no kids for it, again quit. But in the diagram, C can have two kids, this one and this one. So F4 and G2. F4 and G2, that's how we evaluate it. Now we select the operator here. G2 is less than C4. We bring G2 here. And we check if G2 is the goal. No. If it has no kids, quit. But it has kids, and the kids for G2, according to the diagram, is L9 and M7. So why we put L kind of alphabetically? So L9, M7, F4, D4, B5. Now L is the goal. No. Likewise, L can be checked. And I mean, we select the evaluate operator, and we say M7 is less. We take M7 and L9, F4 as it is D4, B5. Now, M is the goal. No. M has kids. Yes. So we process it. We will have M will have R2 and Q1. Then we check, select the operator. Q1 is less than R2. It comes before this one. So Q1 is the goal. No. Q has kids. No. Q hasn't kids. So here stopped. But we missed the goal. That was the goal. The L is goal in gray color. So that's hill climbing. So we couldn't find the goal. So this algorithm might not be, is not complete, and it cannot be optimal, but it's easy way to work with, and it can be modified or upgraded. And there are research on this work as well, so that they can improve. So major problems of hill climbing is that sometimes we got stuck at local maxima. So we might have, we can have in here, or we can have here, local maxima, false hill. Search method without backtracking. There's no backtracking in this case. So remember, we are in Q1. And Q1, there is no kids, but we cannot backtrack to here. We cannot backtrack to here. We cannot backtrack to here, so that we can go back somewhere else. If we backtrack to here, we can try to check this L9. So there's no backtracking, and may be going to infinite path. So if we go all the way down, we might get into loop. Okay, so that's more or less about this algorithm. If you have any problem on this algorithm, you can check my website, and there will be some other algorithms that you can work with. So thank you very much. Stay tuned for the next algorithms. Bye.